Okay, for this one here, it's the same issue. I've been given a derivative, but I don't know the point. This one I can actually separate and integrate. Okay, so we'll do that afterwards, but let's use our linear approximation first. Okay, so for linear approximation, I need an x and y coordinate on the y graph. Okay, and I need to find the slope. So I'm going to calculate dy by dx at x equals 2, y equals 1. It's going to be 2 times 2 square root 1. Okay, so the slope then works out to be 4. So I have now slope. I have an x and y coordinate. So my linear approximation equation is going to be 4x minus 2 plus 1. So this is my linear approximation formula. And I'm going to use this formula to estimate the y value at 2.1. Okay, so I'm going to end up with, okay, this is going to be equal to, looks like it's going to be plus 1. So the y coordinate looks like it's going to be 1.4. Okay, so that is the estimated value at x equals 2.1. So the coordinate that we're saying is that at 2.1, y is approximately 1.4. Okay, so this is our approximation. I better make sure that's clear. This is our approximation. This one happens to be a separable differential equation. So we're going to separate this and actually solve this. Okay, so this is part B. If I actually solve this differential equation, I'm going to end up with dy over root y is equal to 2x dx. Integrate both sides. I'm going to end up with 2 square root y. Okay, on this side, anti-differentiate this, I'm going to end up with x squared plus c. I should solve for the plus c. I need an x and y coordinate on the actual curve. Well, that point is on the actual curve. So plugging that in, y equals square root 1. Okay, square root 1 equals 2 squared plus c. Solving for c, looks like c is equal to negative 2. So the differential equation, when I solve this, looks like this. This is its implicit form. Okay, so let's actually solve this for y. So y equals x squared minus 2 divided by 2 all squared. And if I want to actually calculate the y value at x equals 2.1, okay, so the actual value is going to look like this, 2.1 squared minus 2 over 2 squared. So punching that into my calculator, let's see what the calculator comes up with here. So 2.1 squared minus 2 divided by 2, okay, and that all squared. I'm getting 1.45. Okay, so our actual value of this is equal to 1.452. Okay, so the actual value, so this is the actual coordinate is 2.1, 1.452. Okay, so this was, it looks like it was a concave up graph because our estimation was below the actual value, but in fact the estimation is pretty close. And again, the reason why it's close because as we get zoom into any curve, it starts to look more and more straight. So as long as we're close enough to the point of tangency, the tangent line can approximate values on a curve. Okay, this is what we do with linear approximation.